Okay, so we're kicking off section 8.3, talking about applications in physics and engineering. And our first application that we're going to talk about here is force due to hydrostatic pressure. Our objective in this video is to define and calculate force due to hydrostatic pressure on a solid that's submerged in water. This is the first of our survey of applications that we'll explore. And I want you to keep a careful eye out for any that happens to overlap with your major, field of study, or future career. So I have here a diagram, a very rudimentary one, of a solid that's been submerged in water. And really this is true of anything that's submerged in a fluid, but we typically only care about the case in which it's water. But a solid that is in this position that is not moving, so it's static, it will experience a force due to hydrostatic pressure. So you can imagine that there are tiny arrows representing the force or the pressure that's being experienced by this solid, and in general, hydrostatic pressure is a quantity that is dependent on the medium that you're in, so water, and the depth at which you are in relative to the surface of the medium. So in this particular context, the pressure function due to the being submerged in water is roughly can be represented using actually this, hang on. I'm going to go more generally. Rho G D, where let's quantify these things. So rho is the density of water or the medium. So how much mass per volume. Water is actually a famously dense medium, and its density is defined as 1,000 kilograms per cubic meter. G is the gravitational constant of the acceleration due to gravity. So we've used that before. That's roughly 9.8 meters per second squared. And D is the depth of whatever sliver we're talking about. So specifically here, if we imagine a little sliver of this solid, if we think of it approximately as having the same depth di, so each component with a depth di, we find that the force component, so the force that it experiences along that side, is going to be equal to the pressure times the area of that strip. And the pressure then is approximately 1,000 G di di star. So we're picking a sample point in that strip, and that's going to be times the area of the strip, which in this case we're going to think of as the width as a function of the depth to the width at that point times delta d. So we're going to assume that the width of the height of this little strip here is delta d. Now, this means that if we can break down this solid into little strips, then the total force, use this, total force due to hydrostatic pressure. Notice that this changes at every strip depending on how wide it is, depending on how deep it is given by this integral, the force of the initial depth, which we could call, A, the final depth, which we could call B, times 1,000, or actually, let me use the more general form, because rho G D times the width at that depth D, and it just occurs to me that we should use a different variable because D is overloaded here. So why don't you use T to represent? No, that also isn't good. Just because, in physics we use T a lot. So I'm afraid I'm going to have to use Y. Y is going to represent depth here, times the width as a function of Y times dy. Okay? And importantly, because we are always working with water, this being 1,000 kilograms per meters cubed times 9.8 meters per second squared, is also a quantity that we call delta, which is approximately 62.5 pounds per cubic foot. And we're going to use pounds here to represent weight. All right? So even though I started out talking about SI units and we're using imperial units, the meaning of delta actually doesn't change, but the physical constant that goes in front does change. So let's do this, let's see an example. So we're going to see an example here. So we're going to find the hydrostatic force on one end of a cylindrical drum. We're going to assume right cylindrical, but it doesn't matter. With radius 2 feet, if the drum, pretend that says drum, sorry, is submerged 5 feet deep. So let me draw a diagram of what we're talking about here. So I'm going to put the axis, the origin of this coordinate plane, right at the middle of the drum. I'm going to draw my drum, which is, one end of it is a circle of radius 2. So here's 2, here's 2, here's -2, -2. Okay, and then this is my x-axis, here's my y-axis. And so notice that the level of the water that we're actually talking about is somewhere up here. I guess I could use a little light blue again. So the level of the water is somewhere up here, okay? Where, let me use a different color here. The distance between the center of the drum and the water line is going to be 3 feet. So it looks a little inaccurate, doesn't it? You know what? I'm going to go ahead and just bring that water line a little down here. Let's bring it down to here. That looks better. Okay. Because I want the difference between the water line and the middle of the drum to be 3 feet. That makes the difference between the water line and the bottom of the drum to be 5 feet. And so here's what we're doing then. If we want to imagine that there's a little infinitesimal strip that we're interested in, okay, ultimately our integral is in y, but we need to use the proper counting of depth. So what we're going to think about then is, if depth is properly this distance, this is di for the horizontal strip that we're talking about, then here di star is going to be 3 minus yi star, okay? So if yi star is the actual y, the actual y component of that sample point, then di is just going to be the difference between 3 and y. So this is the depth of the ith strip. What this will allow us to do is to then convert our integral into something involving y. So think about what the width must be as a function of y. So the width is how x relates to y, or 2 times x. How basically we're talking about the edge of the horizontal strip here, right? And so we know that given x sub I star plus y sub I star, both of them squared, equals 4, the radius squared. And that means x sub I star is going to be the square root of 4 minus y sub I star squared. And the width actually is going to be twice xi, okay? So the width of that strip is 2 times x sub I star, which is 2 times 4 minus y sub I star squared, square rooted, okay? This means then, now we can set up our infinitesimal force. So, or sorry, my sample force here. F sub I is approximately delta times d sub I star times omega of y sub I star times delta y. I'm putting that all together. Remember that delta is the 62.5 pounds per feet cubed times delta I, which is 3 minus y sub I star, times the width, which is 2 times the square root of 4 minus y sub I star squared, times delta y, okay? And then the infinitesimal, right? So remember, what are we getting here? We're actually going to be forming the integrand for, for this integral, okay? So we have the form already. Now we're just going to put it into the integral form. So then f is the integral from, and then keep careful track of what the limits of integration are here. Y is going to range between -2 and 2. So we have -2 to 2 of 62.5 times 2 times 3 minus y. I switched the 2 and the 3 minus y, just to make it clear that 2 is a constant, and that's going to be pulled out there. And then times 4, square root of 4 minus y squared dy. And here's where we're just going to split it into, we're going to go ahead and drive right into splitting this into one integrand that's going to have the 3 times this, and then the other one that's going to have the 3 times this, okay? So the first one is going to be 125 times the integral from -2 to 2 of 3 square root of 4 minus y squared dy plus 125 times the integral from -2 to 2 of -y square root of 4 minus y squared dy. Okay, before you panic and you're like, oh, okay, so we're going to have to do some trig substitution and a whole bunch of other stuff, right? Here's what we can do. So first of all, notice that this is an odd integrand. Okay? And we're integrating from -2 to 2. So we're going to use the odd integrand property that says that this integral, because we're evaluating at a and -a, is going to give us the whole thing is equal to 0. Great. Okay? Now this one I'm going to pull out a 3. And what I'm left with is I'm going to be given the area of a semicircular disk of radius 2. Whoops. Meaning, I don't have to resort to integration at all. I'm just interpreting this as a geometric statement. So the 125 times 3 times the integral from -2 to 2 of square root of 4 minus y squared dy. I'm saying that we're saying that is the area of the semicircular disk of radius 2, which, if we apply a geometric formula, this becomes 1/2 the area of that corresponding circle. So 1/2 times pi 2 squared. And then putting it all together, 750 pi. And this will have units of pounds, okay, because it's force. All these calculations have the same sort of flavor to them, so I'm not going to belabor the point and do another example here, but just be aware that some of the critical pieces of information here are being able to skillfully transition between talking about the depth and the variable of integration y, as well as being able to carefully find the width formula for that horizontal strip. And in the next video, we're going to talk about a different application, this time corresponding to center of mass.